So sources of antibiotics and antibiotic resistance. So how do they get into the environment? How do we find them now that we know that they're a problem? We've been manufactured. How do they get into the environment? Well, one of the big things that they get into the environment is just kind of shows you all the different pathways, how it gets into our drinking water, our groundwater, our soil. A lot of it is, so if we look at medical production for humans, it comes out either through we undispose of our medication through our toilets, or improperly use of them, or we just goes through excrement. So if we take in antibiotics, not all of that antibiotic is used. So a certain percentage of it is a certain percentage of it just comes out into our feces, and so that gets into our wastewater treatment plants. So the whole purpose, and you'll learn more about this, the whole purpose of wastewater treatment plants is to decrease that amount of organic material, and you use bacteria to eat the organic material. Well, antibiotics are antibacterial, so a lot of times they survive inside of a wastewater treatment plant. The effluent from the wastewater treatment plant is disposed of into surface water. That can get into our groundwater. It can get into our drinking water supplies. Pharmaceutical productions can have waste that comes out into these things. And then there's also animal use in animal husbandry. Again, their excrements can go into manure ponds, which get into our soil and get into our groundwater. And so there's many different ways that these antibiotics are getting into our environment. So what are antibiotic-resistant genes found? Well, where are they found? Well, they are found everywhere. So we find them in hospital wastewater. We find them in animal production facilities. We find them in leaking sewer lines. WWTP stands for wastewater treatment plant. It's found in surface water, groundwater, drinking water. We find these resistant bacteria everywhere. And so this is a major problem when they are found all throughout our environment. When we look for antibiotic-resistant genes, where do we find them? This is just a study that was done, and they show that it's all throughout the world, and they can find them wherever people are. Antibiotic use in developing countries can be very interesting. So a lot of antibiotics in developing countries are available what's called OTC, which stands for over the counter. So you can walk in and just purchase them in there. Now, as of 2011, you can't purchase antibiotics in Mexico without a prescription. You know, people used to say, oh, just go down to Mexico and pick up tons of penicillin or antibiotics. Now you actually have to talk to a doctor, or you have to talk to a physician's assistant. You have to have a reason you need antibiotics. You have to have testing. So this is not something where, you know, you just cross the border, pick up the drug. There's other drugs you can pick up that way. I mean, really, honestly, sometimes I wonder, like, I can pick up inhalers for friends, and they cost like $1 or $2 down there, versus here where you need a prescription. You know, who's going to take an inhaler except for somebody who's got asthma? The cost, so poor patient compliance, so they only take 1 to 2 days of their drugs instead of taking the whole amount of it. Cost, so some of it's subtherapeutic course, so we're not taking all of it because it might cost so much, so we might not take all of the antibiotics that we need in order to really get rid of it in there. And so these are some of the issues, is cost and then compliance. So if you're not going to see a doctor and you're not explaining that you need to take the whole course of antibiotics even though you feel better, this causes antibiotic resistance. And then low quality. Sometimes some of these things are counterfeit or adulterated, and then people are taking them, and it can actually cause more problems with antibiotic resistance. Human inputs, so excrement of therapeutic antibiotics and metabolites, so many discrete directly to in amounts, so we directly in the amounts of 40% of what we ingest. So what we take in, 40% of it just comes right outside of our feces and outside of our urine. And so it's getting into our waterways because of that. There's disposal of unused antibiotics. So you should never just flush things down the toilet. I think that this is starting to become more and more apparent. People are talking about drug buybacks. Don't just flush them down the toilet to get rid of them. Wait until there's some sort of pharmacist will take them from you. Washing topical applied antibiotics. So you get Neosporin and you put that on there, and then you wash it, it gets into our waterways because that contains 3 different types of antibiotics inside of it. It can go into our septic system or our wastewater treatment plants. It's not very effectively removed because, again, bacteria are what it's against, and that's what's in there. That's what degrades a lot of our organic material inside of our wastewater treatment plants is bacteria eat it. And so if you have antibiotic resistance, it's not going to eat it. So wastewater treatment plants turn into an effective breeding ground for it. So is this found in our waterways? Well, this was kind of a seminal paper that came out in 2002. So it's a little bit old, but this really changed the way people think about it. So 1 or more antibiotics were found in 48% of the streams sampled. So this was a study done by the USGS, and they sampled across the entire country all these different streams. And of those streams, almost half of them had at least 1 antibiotic. 14 of 22 antibiotics detected at least once, so they tested for 22 different antibiotics. They could find 14 of them, at least found them once somewhere around the country. Concentrations are very low, so 0.5 ppb. So very, very low concentrations. The most commonly found ones were things like erythromycin, linctomycin. Antibiotics was found in streams downstream of urban areas and livestock activities. Veterinarian inputs, so this is where you're used for livestock, was early as the 1950s. So they're used to treat infections or to improve growth and feeding efficiencies. So we can use them therapeutically. So if they have an actual disease, they have an infection, you want to keep that cow alive and it's sick. You put a lot into here is antibiotics administered to herds or flocks so that decreasing morbidity and mortality. We can put them for prevention so that if you've got high risk things, you just give it to them. They show no sign of disease, but they're at risk, so we're just going to give it to them. But the main thing that they use them for is growth promotion. So they're putting it into animals in order for them to grow bigger because now they don't have to fight the infection. And so since their body's not fighting an infection, now they're actually fighting off the, they can build bigger and bigger muscles. I mean, if you don't know this, but temperatures of humans have gone down since they first were recorded back in the 1860s when they started doing lots of measurements, and we're cooler now. Well, one of the hypotheses of why our body temperatures are actually cooler now than it was not at 98.6 but is actually closer to 97.4, 97.5 is because we're not fighting infections in our bodies. We fight them other ways, and so our body temperatures don't need to be elevated because heat kills off bacteria. This is why you get a fever. You get that fever because once you get to higher temperatures, these bacteria are generally mesophilic. They like room temperature and everything like that, but once you start getting up into those higher temperatures, it kills off the bacteria. This is why a fever is actually a good thing. It's killing off the infection that's happening. It's your body's way of saying, I need to kill this thing. And so by lowering our body temperatures down a little bit, shows that we're not having to fight infection as much anymore. Antibiotic input into aquatic environments happens from manure. So here is all of our confined animal feeding operation. We have tons of these around here. There are 4 pigs to every person in this county. And so we have tons of these pits all over the town in this area. And so a large fraction of medicines don't get changed through the bodies, even through the animals and stuff. And so it gets collected into these things, and then we take this manure and we spread it on our farm fields, so we get antibiotics going through there. Tetracycline is used in humans and in cattle, and it's estimated 3 million pounds of tetracycline used annually for growth stimulation in livestock. So that's a lot of tetracycline going on there. And 25 to 75% of tetracyclines administered to animals are excreted in the active form. So this is the active form. It's not even changed with inside of the human, with inside the animal. It just comes right back out right as tetracycline, really active. Because sometimes these compounds will get changed when they go through the body, but not this. This just goes right through and right straight through. So antibiotic use in animals, these are the different types of antibiotics that are used. There's different ones. There's different times when different antibiotics are used. And so it's all different classes of antibiotics are used for that. And decreasing concentrations of antibiotics in the environment. So composting of animal manure has been shown to decrease the amount of antibiotics. So if we compost that manure, we let it sit, especially with sunlight, it'll start to photodegrade in there. So if we spread it out, it will degrade with time. Abiotic processes, like I said, so sunlight decreases it. Also sorption. So remember we talked about sorption, that's when something sticks to something. That sorption decreases the concentrations of the antibiotics that are in there.